Hi, this is Sung, your online maths mentor, and now we're moving on to the next theorem that we're going to be looking at, and that's Theorem 4, which says that the angle subtended by an arc or a chord at the center of a circle is double the angle subtended by the arc or the chord, or the same arc or the chord at the circumference of a circle. So this is basically what it's saying, all right? So if you've got an arc or a chord, let's say AB is your arc or your chord, right? And the angle subtended at the center is going to be twice the angle at the circumference. And mind you, it can be anywhere on the circumference pretty much, as long as it's in the same segment, okay? So any point along the circumference, as long as it's in the same segment, will be half that of the angle at the center. Okay, now that's what we've got to try and prove. Now that's the theorem, and that's what we've got to try and prove. Okay, so let's have a look at how we might go about doing this. All right, cool. So here's what I would do. There's going to be different situations, right? There's going to be this situation, and then we're going to examine another two different situations as well. Okay, so just don't think that this proof, that if I prove it with this situation, it's going to prove all the situations. It might not. Okay, so but let's have a look at how it works with this situation. All right, so let's have a look. Here's what we're going to be doing. I'm going to draw or produce, which is the proper mathematical geometrical term. I'm going to produce a line or an interval from C to O and through O. Okay, do you see what I've done? All right, now what that allows us to do is call this angle, say alpha, and this angle beta. That's alpha, that's beta, okay? Now, can you see that if I actually go about showing that this angle's alpha and this angle's beta, we start with those assumptions, if I can actually show that this angle is 2 alpha and this angle's 2 beta, then the proof the theorem actually proves itself. We can actually then say that the angle AOB, which is 2 alpha plus 2 beta, is going to be double angle ACB, which is alpha plus beta. Can you see how that would work? All right, so how do we then go about showing that alpha is equal, that this alpha here is going to be doubled in this angle here, and how do we show that this beta here is going to be doubled in this angle here? Well, let me enlighten you, okay? Here's what we do. We basically can see that this triangle here is an isosceles triangle, yes? Which means that that angle, that side, is equal to that side because it's the radius of a circle, yeah? Which means that that angle there is equal to that angle there, alpha, okay? And again, this beta here will be equal to this beta here because again, you've got an isosceles triangle, yeah? And then using, can you see what's going to happen? That beta and that beta, using the external angle of a triangle theorem, that beta plus that beta is going to be equal to the external angle, right? Because the external angle of a triangle is going to be equal to the sum of the two remote angles. Okay, we did that in the 2-unit course. And again, the same thing here. That alpha here plus that alpha here should give us 2 alpha there. Got it? So that's basically our proof in a nutshell. Okay, let me then go away, write that proof up for you so you can see what's going on. Okay, so our aim is to prove angle ACB is equal to 2 times angle ACB. Right? So we're trying to show that angle AOB is 2 times angle ACB. Does that make sense? Okay, so the first thing I'm going to do is produce a line. So produce CO or CD through center O to D. All right, so that's the first thing I'm going to do. Okay, yeah. And then I'm going to set things up. Let angle ACO be alpha and angle BCO equal beta. Okay, good. So in triangle ACO, OC is equal to OA, radii of circle. Therefore, triangle ACO is isosceles with base angles, angle ACO equaling angle CAO alpha. Similarly, in triangle BCO, similarly in isosceles triangle BCO, we have base angles BCO equals angle CBO equals beta. Got it? Cool. So from triangle ACO, angle AOD equals to 2 beta, 2 alpha, because external angle of triangle theorem. So in other words, alpha plus alpha. Does that make sense? And from triangle BCO, we've got angle BOD equals to 2 beta. Okay, and that's because angle BCO plus angle CBO equals to beta plus beta. Therefore, angle AOB equals to 2 alpha plus 2 beta, and angle ACB equals to alpha plus beta. Therefore, angle AOB is equal to 2 times angle ACB, i.e. Does that make sense? All right. So in other words, theorem 4 is true for this case, simply because we use the external angle of a triangle theorem, which says that that alpha plus that alpha gives you 2 alpha, that beta plus that beta gives you 2 beta, and they're both equal. These two angles are equal because they're isosceles triangles, where the radii are equal, so they're the base angles of an isosceles triangle. Similarly, these two angles are equal because they're the base angles of an isosceles triangle. Using the external angle of a triangle theorem, this plus this should give you that, and that plus that should give you that. So this angle is going to be twice that angle, and that basically is the proof for this particular case of this theorem. All right, I'll give you another case to look at, but in the meantime, I'm going to pause here and set up the next the rest of this episode. Thank you. Hi, this is Sung again. Welcome back. I want to go through another case that you might see where the angle at the center is still going to be twice the angle at the circumference, right? But it's a different situation that we need to prove, and that is this. Basically, where you've got the angle at the center being making one triangle, but that arm also extends to becoming a full diameter, and that arm goes through the center, and it also creates another triangle at the circumference. Does that make sense? All right. So that's basically the second situation that you might encounter. Right. The third situation that we're going to encounter is where this particular where the circumference is way over here, and you've kind of got a different situation altogether. Okay. So with this particular scenario, or this particular case, it's actually easier than the one before. We are again going to use the external angle of a triangle theorem. Basically, we're going to let that angle equal alpha, right? Which means that that other angle is also going to be equal to alpha, because you've got a isosceles triangle where the radii of the circle are the two equal sides, which means that the base angles are both equal. They're both equal to alpha. Using the external angle of a triangle theorem, that alpha there and that alpha there add up to give you 2 alpha over here. Does that make sense? Really, that's, if you understood the first scenario, the proof of which is over here, this scenario is going to be a piece of pie. It's going to be half. It's going to be half as complicated, right? Given that, that's your theorem there, right? Or that's your proof there of exactly what I just described, right? So basically let AC be equal to alpha, right? And in triangle ACO there, because these two sides are equal, you've got an isosceles triangle with base angles ACO and CAO both equaling alpha, right? And from that triangle, you can also work out that AOB, the external angle, is going to be equal to 2 alpha because it's the sum of the two remote angles, right? Which is what I've got there. Okay, cool. I'm going to pause there, set up the next case, right? Which is probably the most harder to see of them all, but it's really not that hard. And then I'll go through that with you soon. All right, thank you. Bye. Hi, welcome back. Thank you for being patient. I commend you for your patience in this episode, because in this part, basically what I want to do is go through the third type of situation, and that's the situation really where the angle at the circumference is like way over here, and then the angle at the center sits outside of the triangle that's made at the by the angle at the circumference. Okay, so we've got to now prove that the angle at the circumference is still twice the angle at the center. All right, so in other words, what we're trying to prove is that AOB is twice ACB, right? So that's basically what we're trying to prove. We're trying to prove that AOB is twice ACB, and we're still trying to prove that, okay? Let me set up how we do that, and you can probably see how I've basically started this proof off. I've started this proof off by producing the line CD through O starting from C, so I've produced that line there, right? That's going to help us out, all right? And the next thing I want you to know is that that actually creates for us two isosceles triangles, right? The first isosceles triangle is this one here, AOC or COA, right? That one there. And can you see that you've got those two sides that are equal? You've got, because they're both radii of a circle, right? See that triangle's an isosceles triangle. Can you also see that the other isosceles triangle is this one here, which is the really long obtuse triangle here, which is CBO, all right, or I've written it up as COB, right? And it's that one there. Can you see that? All right, and I've basically set up in this proof, I've actually proved that those two triangles are isosceles, and I've gone one step further to basically say, let the base angles for the first triangle be alpha, all right? Yep, and then the base angles of the second triangle be beta, all right, which is that angle there and that angle there. Does that make sense? Okay, cool. Now, here's what I want you to note. We're going to use this information to find our two angles, all right? So let's start with this one here, ACB. Angle ACB is actually going to be equal to angle, right? ACB is actually going to be equal to angle ACO minus angle OCB. Does that make sense? Yep. And the reason why is, of course, it's adjacent angles. All right. So what that gives you is alpha minus beta. All right. So angle ACB is going to be alpha minus beta. Got that? What we now got to do is we actually got to work out this angle here. Okay. So let's work out this. So this blue angle here is going to be alpha minus beta, and we've got to actually work out this angle here now. And the way that we do that is we basically work out this angle here minus that angle there. All right. So can you see that angle? What is it? AOB is going to be angle COA, COB minus angle COA. Does that make sense? And that's going to be the same thing, adjacent angles. Beautiful. Now, angle COB is going to be 180 minus 2 alpha, minus 2 beta. Okay, and it's basically the angle sum of a triangle. And it's which triangle? COB. Got it? And angle COA is going to be 180 minus 2 alpha, which is angle sum of triangles COA. Got it? All right, so angle AOB is going to be 180 minus 2 beta minus 180 minus 2 alpha. When you simplify that, these two cancel out. You're left with 2 alpha minus 2 beta. Yeah? So we've actually gone ahead and proved that this angle here is twice that angle there. Okay? So we've actually gone and proved theorem 4 for this particular case as well. Okay? So let me just write up here. Therefore, angle AOB is equal to 2 times angle ACB, which is equal to 2 lots of alpha minus beta. Therefore, theorem 4 is true for this case. Got it? Beautiful. And that basically is the proof for all 3 cases of this theorem. Thank you very much for watching.